All right, so we're going to talk about energy and power now, mainly power, but they're related. So what is power? You've probably heard of power before. What power really is it's a measure of energy per unit time. Typically, we measure it in joules per second, joules being the unit of energy and seconds being the unit of time. And that unit, joules per second, is the same unit as the watt. So when you hear kilowatts or gigawatts, you're talking about thousands, or in the case of megawatts, millions of joules of energy per second, either consumed or dissipated, right? Let me grab my pointer here. It tells us the rate of energy, right? Power tells us the rate of energy consumption or production. And so if we say that something is consuming 10 watts, that means that it's consuming or dissipating 10 joules per second of energy. If we say that something is producing or supplying 10 watts, that means that it's sending 10 joules per second or 10 watts into the circuit. So for example, a current source or a voltage source, we call them sources because they're sources of energy. Right? So if I have a voltage source, I think it's probably just good to do an example. If I have a voltage source here, V, and let's say this is ground, and there's going to be some voltage V across this resistor R, and that voltage V is going to produce a current that flows through the resistor. And so we have these quantities here, V, R, and I. Probably better if I draw V in blue. I like to keep them separate. Oops. Try that again. Okay. We can determine the power dissipated by this resistor by taking the product of the voltage across the resistor and the current through the resistor. Okay, so if I take the voltage across it, multiply by the current through it, that's going to give me the power in watts. That's the formula that I have written right here. And so let me put a little box around that. But there's an important property of this V times I here, especially for DC circuits. Notice, or actually remember, that V is equal to I times R, right? This is Ohm's law. So not only can we calculate the power by voltage times current, we could substitute I times R in here for V, and we get a new equation for power. So if we don't know the voltage, but we know the current and the resistance, we can find power by I times R times I, right? That's me substituting I times R in for V, and that becomes I squared times R. And so that's another expression for the power. Okay? Lastly, if we want to rearrange this equation right here, we can say that I is equal to V over R. And so we could have substituted the I into this equation instead, and we get even another expression for power, which would be V over R times V, which equals V squared over R. Okay, and so those are the three equations that you'll typically see used, and all of them are derived from this initial equation here. Just noting that power is equal to I times V, and recalling that V is equal to I times R for a resistor. You can develop or derive all three of these expressions for finding the power. Okay, so real quickly, let's just do an example. Let's say that this was or actually let me just move some of this stuff out of the way, and we'll just do an example off on the side here. I think it'll be useful. Just throw that over there. Let's just say I've got a 10 volt source supplying a 1 kilo ohm resistor, and I want to know how much power is dissipated in the resistor. Okay, so right off the bat, I know the voltage across this resistor is 10 volts. I know the current through the resistor in that case is going to be 10 milliamps, right? And so since I have all three of these quantities, I could really pick any one of these formulas to calculate the power. Let's just do V times I, since that's the easiest one. Power dissipated by the resistor is going to be equal to 10 volts multiplied by 10 milliamps. And that's going to give me power dissipated by my resistor is 10 times 10 is 100. And then volts times amps gives me watts. So I get 100 milliwatts dissipated by the resistor in this circuit, okay? This becomes really important in the lab specifically because resistors that you buy, like the type that I showed in module 5 of circuits 1, those resistors have a specific power rating. So most of the resistors that you're going to buy will be rated for, I mean, not most, I mean, it depends on the resistor you buy, but if you buy those typical, you know, resistors that have the color bands on them, a lot of them are what's called a 1/4 watt or a 0.25 watt resistor. And so when you design circuits with these resistors, you need to keep this in mind, because if you design a circuit where this power dissipated by your resistor exceeds a 1/4 watt, then the resistor will start to melt. It will just start to burn up and it will cease to behave like a resistor. It will short and you can cause fires. You can melt your breadboard. All kinds of crazy things can happen if you don't pay careful attention to the power rating of your resistor and how much power your resistor is supposed to dissipate in your circuit. Okay, so that's a brief introduction to power. I think it's very easy to do DC power calculations, but the main point of this module is AC power and AC power analysis. So we're going to move into AC power in the next video, but just wanted to give a brief overview on DC power because it's simply just multiplying some of these quantities that you find using Ohm's law across a resistor, because resistors are theoretically the only element that dissipates power, right? Energy is stored in capacitors and inductors. Ideally, they don't dissipate any energy. They just store energy, okay? So we're going to go ahead and end this video, and in the next video, we're going to talk about, start talking about AC power, or basically power analysis in AC circuits.